Hello, everyone. Welcome to the DDPS seminar. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk. But if you have questions, you can unmute and ask questions, or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audience. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me briefly introduce our speaker today. It is an honor to host Alessandro Alla, who is an associate professor at Sapienza University of Rome since 2024. He earned a PhD in applied mathematics from Sapienza in 2014. Before joining Sapienza, he held positions as an assistant professor at Ca' Foscari University of Venice, an adjunct professor at PUC Rio, Brazil, and a postdoctoral fellow at the Florida State University and the University of Hamburg in Germany. His research focuses on optimal control for PDEs, model order reduction, and data-driven modeling. Today, Alessandro will talk about data-driven algorithms for online identification and control of partial differential equations. I'm sure we are going to hear a wonderful talk. Now, let me ask a somewhat informal questions to Alessandro just to get to know him better and make this seminar somewhat informal. Is that okay, Alessandro?
Yeah.
Okay, here you go. So do you have any superpower, like unusual habit or unusual the routines you do, which is distinguishing from others, and helps you, you know, what,
So I was expecting something. I mean, usually if people ask me something like that, I say I do math. But here, I mean, it's not a
Well, that's
superpower.
yeah,
Yes.
that could be a superpower. I mean, I don't know. Why do you think that's the superpower, math?
No, I'm just kidding. No, I do not have a superpower. I'm sorry.
How about the
I'm
interesting
I'm a
habit?
very.
How about the interesting habit you have?
I like traveling. I like traveling.
Traveling. I mean, you are in Italy, so that's the
Yeah.
perfect answer. Any
Yeah.
any favorite place to go?
Well, I spent 4 years in Brazil, so Rio de Janeiro to me is one of the best places in the world to live, to
Really?
spend time. Yeah. Absolutely.
Oh, okay.
Absolutely.
I never been in
Absolutely.
Brazil, so
You
that
absolutely
makes
have to
me
go.
want to go.
I mean, Rio de Janeiro, it's summer all year round. You go to the beach, you can hike, you go to the beach, you can party, you can do, I mean, many things. Absolutely amazing.
Okay, my bucket list.
But I suggest you to go if you speak when you speak Portuguese. So there is a process. You learn Portuguese and then you go to Rio de Janeiro.
Oh, I see. Okay. All right. There you go. The stage is yours.
Okay, thank you very much for this opportunity, and thank you all for being here. Wherever you are, so here it's 7 p.m. So I can say good afternoon, good morning, and good night. Anyway, so this talk is a joint work with Giulia Bertaglia, Elisa Calzola, and Agnese Pacifico, and it's about optimal control when the dynamics is not completely known. So that's why you see also identification. So I'm trying to combine things on data-driven modeling, but applied to control. So before I get into the topic, I just want to advertise a couple of events that we are organizing in Rome that you are very welcome to come and join. So registration is free, so you just have to register. So we will have both are in September. There are 2 consecutive weeks. So if you want to come to Rome and spend 2 weeks, so you have an opportunity, or if you like, an excuse. So one is about a school on scientific machine learning, also PhD and postdoc are very welcome to present short talk or posters, depends on the amount of people that want to do that. And then the week after, we have a workshop on optimal control and agent system. So just feel free to contact me, and also feel free to stop me anytime during the talk. I'm very happy to receive questions to be stopped during the talk. So this is the outline of my talk. Basically, I'm going to split the talks in two parts. The topic is the same, but two different approaches. One is about, for those of you familiar with the SIND, the sparse identification nonlinear dynamical system, the first part, and also it also addresses some reinforcement learning ideas. And the second part is about the use of physics-informed neural network in this context of identification and control. So let's start with the first one, with the first part. Those are the two main references for this part of the talk. Those are the two papers where you find all the details that I'm going to skip during this part. So let me first set my control problem. So you see here we have a dynamics which is given by nonlinear dynamics. So this A is a function of the state X. So X for me in this part is the state, U is the control, and also B depends on the dynamics. And then we have a quadratic cost function that we want to minimize. So maybe some of you that are familiar with the linear quadratic regulator. So in general, you have X dot equal AX plus BU. In this case, this is a generalization where you see that A and B also depends on the state. So here I have all the classical assumptions to guarantee asymptotic stabilization on the matrix A, Q, R, and so on. So to solve this problem, as I mentioned, if you have a linear quadratic setting, usually the control, you can get the control, or let's say the value function solving the algebraic Riccati equation, which is given here. This is a nonlinear matrix equation. And then the control has this structure where you see that you have R and R from the cost functional, B from the dynamics, and then pi from the solution of the algebraic Riccati equation. So in this situation, where there are no constraints on the control, you can exactly solve, and there are many different works on approximation of the algebraic Riccati equation, also for a large-scale problem. So you can use Krylov subspace, you can use Newton methods, but nowadays there are very valid routines to solve this, to approximate this problem, very high-dimensional problem. Then if you want to switch to nonlinear problem and setting with a similar setting to this, you see that now I put in red the dependence of the problem on the state, A of X and B of X. But if you freeze at each iteration, at each time, your current position, you see that you have to solve, you can solve that using a state-dependent Riccati equation. So at the position X, you have to solve, you can get the control for this nonlinear problem, solving the state-dependent Riccati equation. You see that you have exactly the same structure, but that depends on X. So at each iteration, at each position, you have to update the solution of the algebraic Riccati equation. And then you can solve, you can get the control that in this case is just suboptimal because it's not guaranteed that your value function has this quadratic structure just locally. And here you see that you have, you can get the control. You see here the differences are just that the B and pi that depends on the state, on the current state. So you can think about the state-dependent Riccati equation as a model predictive control with instantaneous control. So you freeze and you solve an RQR problem. Nevertheless, you can't prove that this is optimal. This is just suboptimal because what you are doing, you are assuming that your value function can be locally quadratic. So this is an approximation of the value function. And then from a computational point of view, as I mentioned, you have to solve an algebraic Riccati equation at each time in iteration. So this is very demanding. It's very, I mean, my point of view is to solve large-scale problems. So for instance, PDEs. So that means that if you discretize a PDE, a two-dimensional PDE, you easily end up with a a large system of differential equation in dimension 10 to the 4 or even larger. So that means for an algebraic Riccati equation, you have 10 to the 8 unknown. So that's very, very expensive. So in here, just to refer to a recent work with Dante Carisi and Valeria Simoncini, where we address the problem of using state-dependent Riccati equation for high-dimensional problem and in H2 and H infinity control. Okay, let me get into the topic of identification and control. So as you can imagine, my control will be computed using the state-dependent Riccati approach. So now let me think also that my dynamics is not completely unknown. You see here that I'm supposed I'm assuming to have a linear combination for my dynamics. So AJ, those are a bunch of matrices that will build my library, and then I have some coefficients here that are unknown. So I have a library and I have some coefficient. I want to discover these coefficients, plus I want to compute my control. So I have two unknowns, the control and the coefficient. So I want to identify the dynamics, but that I want to control. So this is a classical data-driven approximation, like in a SIMD structure, basically. So AJ, let me stress that AJ are known for all J's, and also B is known. What are our assumptions? So this is almost a reinforcement learning assumption. So we do not know the system, but we can observe the system. Namely, that if you give me an input, U of t, and an initial condition, I can observe the trajectory. So this mu star means that I can exactly observe the problem. So I do not know my mu coefficients, but if you give me U of t, I can observe the dynamics through the trajectory. Okay? So the goal is, as I mentioned, the control of unknown problem. I want to discover on the fly the problem, so I want to identify on the fly, and I want to have also efficient and accurate approximation. So this is a reinforcement learning assumption. But here, in this case, we want to do everything on the fly, so we do not want to observe many times the trajectory. During the talk, I will use mu as a generic parameter, mu star as the true configuration, and mu tilde my estimate configuration. And then whenever I use this coefficient, I want to stress which control. For instance, this control means this is the control which is associated to my estimate parameter. The dynamics here, this is the dynamics that I can observe these dynamics given this control, which is computed through my estimate, and plugged into the system that I do not know. And if I want to stress that I'm using an approximate method, I will put the I here to say that I'm computing at the time ti. So this is the discrete approximation. So again, this is the cost function. I keep the quadratic structure for my cost function. So this is as in the RQR problem. And the workflow is to pick a parameter configuration, so an initial guess. I compute the corresponding control given this initial guess for the parameter. I observe the trajectory. Then I update the parameter configuration based on the observation, and I keep iterating this. At a certain point, I will stop to update my parameter configuration when I see that there is not much difference between two iterations. So now I need to tell you how to compute mu, which is very important. So as I mentioned, I start with an initial configuration. I can compute my control. After I compute my control, I get the trajectory, okay, a discrete trajectory. When I compute the discrete trajectory, I can plug into the system. Remember that I have an ansatz for my trajectory. I have here a linear combination, okay, but I can compute the AJ into the trajectory and also the control. This is feedback control, so I know the structure of the control. So this turns out to be a linear regression problem, basically. So you see on the left, I have this vector, the derivative, and the control contribution, and then my library times my vector. So this is a linear regression problem. And we do solve the linear regression problem using Bayesian linear regression. This is mainly, I mean, you can use whatever you prefer. You can also use optimization or loss optimization, ridge optimization, whatever you prefer. Here, for some reason, based on reinforcement learning, we use the Bayesian linear regression, but the results will not be much different if you use another method. And then again, we learn the system on the fly. So the algorithm works as follows, as I mentioned. So I get an initial configuration, I solve my algebraic Riccati equation, I compute the feedback control, and after that I get the feedback control, I can observe the trajectory, and then I get my update for the parameter using the Bayesian linear regression. We actually put a stopping criteria here to update the parameter configuration when two parameter estimates are very close to each other. We stop the algorithm. Let me give you some tests. So in one of the papers, we also worked using model reduction for this, but here we're not focus on that. So we are just working on one-dimensional. We are just working on one-dimensional PDE. But you see here that we have many PDEs here. You can think having heat equation, advection diffusion. You can think having Allen-Kahn, Zeldovich, KDV, Burgers. So you have many combinations. So you see I have just 7 parameters to discover, but I have many different problems. And from a control point of view, each of them are different features. So if you have a parabolic problem, is different from an hyperbolic problem. So that makes also the control problem not that easy, although we have just 7 coefficients. And sometimes we use zero Dirichlet boundary condition or Neumann boundary condition. That depends on the problem. But you see here that if you discretize this problem, you get into the state-dependent approach. My matrix A of x is this is the discretization of the second order derivative. This is the discretization of the advection term. Then we have the polynomial structure, and then we have the matrix for the third order derivative, or here we have the Burgers nonlinearity. In order to approximate this problem, we use the Jacobian free Newton-Kirchhoff method, which turns out to be very efficient for high-dimensional problem. So let me start with the viscous Burgers. So this is the problem that we want to identify. So this is the what we get out from our observation. This is the problem behind our observation, and you see that we have a low diffusion and we have a Burgers term. So those are some parameters where we control and the dimension of the discrete problem. And you see here that using our method, so this is the true configuration, this is the reconstructed. Here, so this is the diffusion part, this is the Burgers nonlinearity, and all the other coefficients are almost zero, close to zero. I mean, this also depends on the discretization here. So the difference here is below our delta t, so that makes consistent with what we were expecting. And here you see the solution of the uncontrolled problem. So uncontrolled problem means that u is equal to 0. And then here we have you have the solution of the controlled solution. So using state-dependent Riccati equation straightforward for the known problem. And here where we do identification and control. You see that they are pretty similar, but a more precise study is given here. For instance, here you see the two different control. The control U1 and U2 are the control that comes from the state-dependent Riccati equation, so when the dynamics is known. And when you see RL, so this is our approach. You see that they're pretty similar. Here there is a difference, but that was our choice to start with U equals 0 at the beginning. You are free, I mean, basically you are free and you can get even better result. Here you see the convergence of the parameter configuration. At the beginning it's very changing a lot, but then it's converging to a certain configuration. And here the evaluation of the cost functional. As expected, the cost functional for the state-dependent Riccati approach is below, but there's not much difference between our approach and the state-dependent. Remind that in our approach, the dynamic is not known. So we have an error in the identification, which is clearly reflected here. From a CPU time point of view, of course, the uncontrolled problem is rather cheap, but there is no control involved. And here you see that it's rather similar. It's rather similar. That because the amount of Riccati equation that you have to solve, which is the most expensive part in this problem. So you see, this is just a simulation without control. So this is the most expensive part, the solution, the approximation of the Riccati equation, and you have just about 1 second more expensive. Here, it's just a linear regression problem more than here. So I tried to give an idea about identification and control for unknown PDEs using some reinforcement learning assumption where you do not know the model, but you can observe. And on the difference is that we do that on the fly, so we do not get many observations. Basically, I show you numerical convergence for our experiments, and in this talk I did not address, but we also had work on using model reduction for higher dimensional problems. Someone wanted to ask me something?
Yeah, since you're finishing the first part.
The first part, yeah.
Yeah. Okay, cool. So I guess it's a good time to close and then ask questions. So previous examples, how many state variable did you have? Like
it was 121. I mean, this is a one-dimensional PDE, so you don't get large scale.
Oh, but that's the discretized version.
Yes, the discretized.
After discretization, you got the 121.
Yeah,
but
exactly.
Since it's 1D, you have a
one variable. You do not get.
scalar.
Yeah, then in a second word that I'm not going to present here because I want to switch and use the physics informed approach. We also have something which is 10 to the 4th dimension.
Okay, got it. And then
we combine with model reduction in order to approximate. I mean to get something efficient and accurate.
Okay, and then optimal control demonstration you showed. You are assuming this equation is not known, and then you by regressions, Cindy,
exactly,
you identify that.
Yeah, it's basically Cindy applied to control problem.
So in that scenario, what if in the regression you have to provide a set of library, candidate library, and what if some of the essential term is not provided?
Yeah. Well, so what we did here, we didn't address that.
Yeah.
But for us, I mean, I tried to have a more control point of view in a sense that here we have several problems to control basically. And if you think about a control problem, then if you add more terms, that means that maybe your problem is not controllable. Okay, so I also wanted to make sure that I could compute my control.
Right.
Otherwise, I got other issues. And then also from a control point of view here, since you have many different combinations and many different interesting control problems, that I thought that was enough to address this. But I agree. But I agree. I think in general, I mean, if you have libraries, more libraries on not the exact libraries, this approach might not work. I mean, I absolutely agree if that was your point.
Yeah, but underlying assumption you have is, those, chosen libraries by user. Hopefully that includes the true system equation.
Yeah. No, for us, absolutely. We added the true. for us, we knew exactly, it's not purely data-driven in a sense that we knew the structure of the problem, but we didn't, I mean, only the mu coefficient were unknown. But for a control point of view, I mean, I guess it's not that easy to find libraries out of the blue without no information. Because you might end up that the Riccati equation is not solvable, right? So then what do you do?
That's a tough problem.
Yeah, exactly. I mean, that's my point of view, and that's the reason why we got exactly the same library, basically.
Okay, cool. Is there any other question from audience? Because we just finished the first part, and Alessandro will move on to the second part. Before that, if you have questions.
Okay, maybe at the end.
Okay, cool.
Let's see. So now same problem but different approach. Physics informed neural network. I still have about 20 minutes, right? More or less.
Yeah.
More or less.
Yeah.
Okay. So I guess you are all familiar with physics informed neural network. But so before starting, let me just mention that so when we started to investigate here, you see in red our contribution, we found not many works on control using physics informed. Here I'm listing some of them. Perhaps this list is not complete, but I feel that this is still a very open topic. I mean, if you think that the physics informed were introduced maybe 5-6 years ago, I mean, I think it's normal that optimal control with this approach is still very open. So what is physics informed neural network? Physics informed neural network is a way to use to approximate differential equation using neural network, providing physics information. And the physics information means that in the loss function we provide, we want to minimize the residual of the PDE that we want to solve. Here we want to use the physics informed to solve time-dependent optimal control problem in a particular scenario where we cannot use numerical methods. So say that we do not know, for instance, the boundary conditions, initial or final conditions, or just we just have a few data, but we do not know the structure, the continuous structure of the problem, for instance. And also in situation where the state adjoint equation probably are not completely known. So in this situation when you do not know boundary condition or the initial conditions or the state equation or the adjoint equation, you cannot use standard numerical methods. So this is the situation where we are addressing. And of course that also gets into identification because we are assuming that the problem is not completely known, and control because we want to get an optimal control. So what in general we will have, I'm slightly changing the notation. So here we have a state which depends on position and time. We will use a feed-forward neural network with L+1 layers and L-1 hidden layers. We will have some data, some observation, and then the surrogate, the neural network will be written in this way. I will stress the n here. And this parameter theta will be the object of our minimization. In fact, we will have to define different loss functions. So for us, loss function for the data. So if we have observation, for the residual here, and from the boundary, if we have data from the boundary. Okay. So the three loss functions that we're using are data, residual of the PDE, and boundary condition. So in that case, you will get the theta for the surrogate model. And just to stress that if you do not have the residual and the boundary condition, this is a standard deep neural network. So we will use the optimization routine is a classical Adam optimizer. And here I want to stress that F for us, which is the residual here, is not completely known. So we want to identify that. For the state, for optimal control here, I'm not using feedback approach or the state-dependent approach. I'm using the standard open loop. And in open loop, okay, you have a parameter that you want to control here. This is the state equation. And I want to stress that this parameter is not known. So this is the parameter that we want to identify. N will be known, but C here will not be known. And then we have an optimal control here. This is a standard tracking problem, also a quadratic cost function, where we want to get as close as possible to a reference, which is called y bar. So this is a standard time-dependent time-dependent optimal control problem. And if you want to get your control, you can use a Lagrangian function where you identify the cost, adjoint, and the control problem, and you derive the optimality condition, which are usually given the state, adjoint equation, which is a backward linear problem. P is the unknown that comes here, and then the optimality condition that correlate the control and the joint. So our physics, our neural network architecture works as follows. So we assume to have data for the uncontrolled problem to make it more realistic, because usually you do not have data from the controlled problem. So what do we do from this data from the uncontrolled problem? We try to identify the problem. So in the first network architecture, we identify the problem based on the uncontrolled structure. So you see here that our F now does not depend on U. So at the first stage, we try to identify Xi. Once we identify Xi, we set a second neural network architecture. You see here the output is just the uncontrolled, and then after identification, we switch to a control problem, and our output will be state, control, and adjoint, and that's it. So we have two different architecture because we have to identify, and usually you do not get the data from the control problem, and then you solve the optimal control problem. What we minimize are exactly the same, that depends on the data. So here in the second architecture, we use some information. So we initialize our network from using this configuration, for instance, that even though it comes from the uncontrolled problem, you get some feature of the dynamics. And also the loss function here that we want to mean, also the data will be different. Basically, here we do not use data. And here the residual is from the uncontrolled problem. So in our simulations, we will always want to track our problem to 0. Then if I want to indicate the numerical methods, or when I assume to know the dynamics and so on, I will call y of u star to stress that this comes from the numerical method. Whenever the solution comes from the physics-informed neural network approach, I will call y pin and u pin. And if I want to plug my pin control into my dynamics to check how consistent is our result, I will call y of u pin. So y of u pin is the numerical method using the control that comes from the neural network. I want to compute a different kind of control. So the error between the optimal solution and the pin solution, between the optimal control and the pin control, and then also the difference between the optimal solution and the solution using the pin control, so with the numerical method. We will use 5 layers, 3 hidden layers with 64 nodes, and the learning rate for the Adam optimizer is 10 to the -3. In order to weight more our data, so our information, we put 10 in front of the data and the boundary whenever are provided, and just 1 in front of the residual. So first example, again, this is the control of the viscous burgers. just drinking, sorry. So the unknown is this parameter, the diffusion part. This is the initial condition, and this is the boundary condition. So this is unknown and also the control. This is the quadratic cost function, and here for completeness, I provide you the adjoint equation, optimality conditions. So now we focus on two different scenarios. One when the diffusion is 0.5, so which is more parabolic problem, and one when the diffusion is 0.05, so that the advection is dominating. We're just using 10 data. No initial condition is provided, and the boundary condition is just a sparse level. We just have 18 points to check the boundary condition. Where we test our neural network, we have 336 points, and our threshold to stop our method is 10 to the minus 7. So now the problem is diffusive. So in black, in white, you see the point, the data that we are considering from the uncontrolled problem. You see that the initial condition is not considered. And in black, you should see probably, so here, here, those points are the boundary condition that data about the boundary condition. So I'm not providing the boundary condition, I'm just providing some sparse data. And here, so this is from the uncontrolled problem, and this is what you expect from the control problem. You see that the data from the boundary are the same, and this is the initial condition. This is something that you can discover from the network using the uncontrolled setting. So this is the optimal solution, the solution that we expect from using numerical method when everything is known. This is the uncontrolled solution. So you see that it is going to zero faster. It's getting flat faster. And this is the pin solution. I mean, from a visual point of view, you see here that they are pretty similar. This is the optimal control and the pin control. Again, it's difficult to see, to visualize the difference. So here in 0, this is not exactly 0, but nevertheless, they have a very good agreement. So let's try to quantify the error. So all the errors, so difference between the control, the optimal control and the pin control state, optimal state and the pin solution is always about between 10 to the minus 2 and 10 to the minus 3. This is our level of accuracy. And you see here a comparison on the final time. So this is the uncontrolled solution, and this is the 3 different strategies and at the final time, the state at the final time. You see that there is an error clearly, but the neural network it's getting what it has to do. And this is how the diffusion is converging towards the ground truth. So this is the side configuration, and this is how we are converging to the ground truth. Let's go to something which is more advection dominating. Same structure, few data, but you see now how important is the advection here, and also is also clearly how the control is working. So you see that this is going to zero faster than this. In fact, here you have the uncontrolled solution. This is the controlled solution, and again, they are very similar. This was interesting for us because I mean, usually from control problem, if you have an advection dominated problem, this is harder. But nevertheless, even keeping the same order accuracy, which is always something between 10 to the minus 2 and 10 to the minus 3, you can get you can make the pin approach working. So this is a comparison between the controls. And also, again, this is the convergence of the diffusion parameter and the solution the final time. You see here the error behavior, but the results are very similar to the previous case. Let's go to Allen-Kahn. So now we have a polynomial nonlinearity, y to the 3. So this control problem is rather interesting because the uncontrolled problem is going, I mean, this problem, the uncontrolled problem has 3 equilibrium, and the uncontrolled problem goes to the stable equilibrium, which is +1 or -1, depending on the initial condition. So if you want to get to the solution to 0, you have to apply, you can apply control. And again, the diffusion is the unknown part. Again, quadratic cost functional, we want to track 0. This is the adjoint, and this is the optimality conditions. And we are using 2 different scenarios. The diffusion 0.1, and we have mu equal 1, so this is an easy case. And the second case is the diffusion is 1, but the nonlinearity is 11. So this is the interesting part from a control point of view. And also we were working with 2 different kind of initial condition, one which was just positive, and the second one which also was changing the sign. And again, we work with a few amount of data, just 12 data for the uncontrolled solution and 14 data for the 12 points for the boundary conditions. Again, we do not use any data from control and adjoint. So all the information that we have comes from the uncontrolled solution. 520 points for residual, and the stopping there is 10 to the -5. You see in white the amount of data that we're using, and in black on the boundary. So same idea, 0.1 diffusion and 1 for the nonlinear term. You see how the uncontrolled problem gets to the sort of steady state here, and the control solution is going to 0. Those are very similar again. The control, we have an agreement, and this is how it looks like the solution on the final time. It's clear the difference between uncontrolled problem and control problem, and here we have the conversion towards the ground truth. The error, what we found, that was always something between -2 and -3. So this was more. So here the uncontrolled problem gets so the maximum, the initial condition is 0.2, and you always get 0.2. If you change this coefficient in front of the nonlinear term, I mean, here it's always similar, the amount of data that we are using. So this is increasing now. The problem is less stable. It's increasing, and you see the control solution that is going to 0. And also the initial condition now changing the sign, which makes the problem a little bit more difficult. This is the control, is very active at the beginning, and then it gets to 0. And again, the convergence of to the desired configuration and the solution at the final time. Error is always between 10 to the -2, -3. So coming from control and numerical analysis, we were trying to understand when to use and why to use physics in formal neural network. Because from accuracy point of view and the efficiency point of view, I mean, accuracy, I understood that something order -3, it's usually accepted, so you can never beat a numerical methods. Efficiency, there are numerical methods that are very efficient nowadays, also for high-dimensional problems, so the use of neural network does not make very efficient. I mean, straightforward this approach. So we were thinking when to use that. So situation where you do not know the problem, you have just a few information, then physics in formal neural network, in my opinion, is very interesting and is very useful. Otherwise, you cannot do anything. So this in the paper we wrote a very long conclusion where we were addressing all these questions. That's something that something during the talk I I somehow addressed, and we were, I mean, that was our interpretation. So this drives me to the conclusion. So in this second part, I was presenting something about extension of physics-informed neural network to control problem, where the control problem is not completely known, the dynamic is not completely known. So we were using this approach to identify and compute control. So with that, I really would like to thank you for your attention, for being here till the end. Thank you.
Thank you so much for the nice talk, Alessandro. And I loved it. And especially this slide, you know, some comments and the conclusions about the pins and giving us some food for thoughts. And I guess it's a trap for the questions from audience. They can use this one.
Yeah, I mean, also if you are not familiar with control and you want to share your experience, so maybe I do not come from neural network, and but I mean my experience was always this kind of error. So if you have a better experience or suggestions, I'm very happy to hear your opinion.
Which captures more or less, you know, similar experience I had with the pins as well. As you said, you know, traditional numerical methods, in terms of accuracy and speed, probably it outperforms the pins, and that's what I have seen it before.
Yeah.
But if you don't have anything, any data, maybe pins is the only options.
Yeah.
You can use.
So honestly, I started to do a very simple problem, linear it equation, using pins with it equation, no control, and I was getting 10 to the minus 3, nothing better.
Yeah. There's a convergence issue with the pins.
Yeah,
and
I was not able to get any convergence, like you know, I mean, I was expecting to have, I mean, I don't know, maybe I have more layers, more nodes, more data, something. I mean, I was not able to get some order of convergence out of that, which made me, I mean, maybe I made a mistake, I don't know, but
no.
Looks like this is the trend, an accepted common trend.
I mean, yeah, that's that too. Like a lot of trial and errors you have to go through, you know.
Yeah, exactly. Yeah,
results.
exactly.
It's humongous. Okay, Boris, yes, please.
Hi everyone. Hi Alessandro. Thanks for a nice talk.
Hi, Boris.
I had a question on your the first part where you showed I didn't ask it at that point, but where you showed convergence of the control signal and then convergence of the energy. Or
in the first part, right?
Yeah, in the first part, yeah.
Yeah. This slide, probably.
Yeah, exactly. So somehow the difference in the control doesn't seem to be, or how am I interpreting the differences in the control coming from RL and the U1s and U2s that you have computed? They don't seem to show up in the cost function. Is it so? What's your weight on the control? That was my question, I think.
So it reflects in a sense that this is more it's a little bit higher than this one. So, but what you see here is just it's just at the first iteration. This is our choice to put u equals 0. Okay, but then at the second step, I mean, they are pretty much matching. You see, so it's just the first at the first iteration that there is this difference, and then if you think about the cost, you paid 0 at the beginning at the first iteration, right? Because of the choice,
right?
So that is maybe the reason also that is not expensive. But
okay, now I see it. Yeah, now I see
it. In the paper, in the paper, I think we also addressed that, and we did in one of the two papers. I think in the second paper, the one with using model reduction, we did not do starting from 0. Okay, so you do not even see this discrepancy.
Okay, yeah, fine. Yeah, just wanted to clarify and see that I understood the figure.
Yeah.
Okay, thank you.
You're welcome.
Any other questions? So are you planning to, apply this to like a higher dimensional system, like the 2D, 3D?
For using, well, for this approach, we have done for two-dimensional PDEs. Not fancy PDEs. So if you ask me if I did for Navier-Stokes or like something for fluid, I haven't done that. For pins, I don't know, because two-dimensional PDEs, that means that it's very expensive from a computational point of view. So I think something has to be done to make it more efficient. Otherwise, it's very, very costly, in my opinion.
Yeah.
Because I mean, it's not just one PDE. We have two PDEs to solve, basically. Use adjoint and state. So it might be very expensive, in my opinion.
Yeah.
But if you have references to make it more efficient, I'm happy to receive.
Yeah. Well, I mean, really impactful application for the, in general, control problem is robotic control.
Yeah,
right?
sure. No, I'm just thinking like in general, in a sense that if you have a 9-dimensional problem and you want to use neural network, at least straightforward in this way, I mean, it can be very expensive.
Yeah. I mean, the reason I brought up the robotic, I mean, I don't have experience with it. Maybe Boris has some experience with the robotic control. And there, the number of variables you treat is not that high, right? It's not we are not dealing with like thousands or millions of degrees of freedom, which comes.
No, with the robotic, you can. I mean, I think robotic, you can. I mean, you can get different levels of dimensions, basically.
And how do you see the application of that, your first approach, like using the sparse regression, Cindy, incorporating in the optimal control and apply that to the robotic applications?
I mean, I would say, I mean, I do not know the structure of the robotic, I mean, the equation comes from the robotic force. So I don't know, I'm not sure if you can get, I mean, probably you can write in a setting as a state dependent. So the key point is not the control, in my opinion. The key point are the libraries for this approach in general for Cindy. So if you have information about the libraries, I think it's pretty doable.
You mean like the variable library? Is it known?
Yeah. So what I call AJ in this part.
I guess those system is not known in general in robotics. I don't know, Boris, if you can comment on that. So in that case, if it is not
that means so you are thinking about something like purely data driven, that you don't really
exactly.
So you just have data.
Yeah, but use the Cindy to identify some sort of surrogate model. It does not have to be exact governance.
Yeah. I mean, but that I would say that from that point of view, the key point is the libraries. Then everything is doable. In my opinion, I mean.
Okay. Pratana, you have a question, right?
Yeah.
Hands up.
Hi, Alejandro. Yeah, thanks for the presentation. So I was wondering, which optimizer did you use for the pins problems?
Adam.
Okay. So in our test cases, we were using Adam and then Adam plus LVFGS, but then recently we found another optimizer called SOAP, which is basically shampoo with Adam in the p-conditioners eigenbasis. So that's giving pretty good result, and it's very computationally efficient.
Can you write the name of the optimizer on the chat, please?
Yeah. I'll
Thank you.
refer the paper.
Yeah. Thank you very much. Yeah, it's also if you have a paper. Thank you.
Yeah. So I'm typing it now.
How efficient is it, Pratana? Like
it's
with
compared to LVFGS, it's almost 10 times efficient.
Faster.
Yeah, and the good thing is that you don't need to use Adam in conjunction with shampoo or soap. You can just use the SOAP optimizer right away. Yeah.
Very good tip. Thank you, Pratano.
Yeah.
sharing.
So I'm also posting one paper from Pedicaris' group, Wang and Pedicaris. I think they tested it on Pin's problem, and for all the problems, they found better results.
Okay.
Yeah.
Thanks for sharing.
Yeah, no problem.
Cool. Is there any other question? If not, let's thank our speaker for the nice talk, Alessandro. It was a very nice talk and
Thank you very much.
very nice numerical results. And thank you for sharing with us. Through this DDPS seminar, hopefully you get more network and connections and
Hopefully,
say future collaborations. That would
Who
be
knows?
wonderful. Okay, well,
Thank
with
you very
that,
much. Bye-bye.
Alessandro.
Bye. Bye, manage.
Bye, everyone.